Hello everyone, welcome back. In this video we're going to solve another example on normal and tangential components, and I'm sure you know that the image tells us that in this problem we're going to include a train in our problem. So let's see what our learning objective is. We'll solve the problem which is falls under curvilinear motion, and we'll solve for normal and tangential components. So in this example, we'll apply the normal and tangential coordinate system to determine the direction and magnitude of velocity and acceleration. This is a train. We'll work on only the engine. So bye to the train, and let's move to the problem. A train starts from a station with increasing speed at 5 meters per second square. The train starts from a station, meaning it may have started from zero position, zero velocity, and the question is how long it will take for the train to reach a magnitude acceleration of 25 meters per second square. So the question asks for how long it will take the train to reach at 25 per meter square acceleration, and what will be the distance from the station. So to gain 25 meters per second square acceleration, how far it will move by the time it reaches 25 meter per second square, and then given rho, which is the radius of curvature, 50 meter. So let's see what are the things are given. Since it says that train starts from station and increasing the speed at 5 meter per second square, so it's the train speeds. It will be the tangential component. Let's use different one. Color. Okay. Tangential component, which is given, is 5 meter per second square. The rho is given, radius of curvature 50 meter, and acceleration that it says the magnitude it reaches at 25 meter per second square. Okay, and how long it takes. So what would be t, and time, and what will be the distance of the train. From the station. So let's draw a diagram. Let us use a different color. Maybe. Okay. So maybe it's the train line. Okay, and this is the train line. And this is our train. The radius of curvature is this point is given, which is 50 meter. If it's the station was here, the station was here, so we can assume that point as our start point, and this is our position right now when the acceleration is 25. So what is the distance d here? That's what we're looking for. So let's move to the solution. solution would be, so we know the tangential component. Let's look for the vertical component to see the acceleration. We know the normal component is the v square over rho, and we know the rho is given. So rho is given. What we don't know is what would be the value of velocity v, this one. So by definition, we know A equals to tangential component whole square plus a normal component whole square equals to our target, which is 25. So we can put this value here. Tangential component is given, so we can plug the value up here. So it becomes 5 square plus v square over rho. We know the rho, that is 50 whole square 25. If we solve for this, we'll get, we take whole square on both sides. 625 equals to 25 plus v to the power 4 over 50 square. If we solve for this, we can get the velocity v equals to 35 meter per second. This velocity, it was the velocity at that point right now. So this is one part. Now let's work for how what is the time. Let's use different color. So now we can use the final velocity, which is 35. Our formula v equals to u, the initial velocity, plus acceleration multiplied by time. So this is what we know by definition, the equation. But what would be the A? Is it the magnitude, which is 25, or the tangential component? Yes, this will be the tangential component AT, not remember, not the value of A, which is 25, because the velocity we're working on at current position is the tangential component. U was the initial velocity, which was is not given, and train starts from a station, so we can assume that it starts from 0. So initial velocity was 0, and the tangential component, we just it was given, which is 5 meter per second square. So, and we found the tangential velocity when the acceleration is 25. We found the velocity is 35. So 0 plus 5 multiplied by t. Now we can easily solve for t, which is 7 second. So it's pretty easy to solve. Only thing you have to be careful about is that you don't take the magnitude A to put it here, but just the tangential component AT. Okay, so the last thing we're missing is that how far it moved from the station to the final point when the acceleration is 25 meter per second square. To do that, we know another equation, which is v square equals to u square plus twice as, or in this case we'll say d, because we're looking for d, and we know u square initial velocity was 0. So 35 whole square equals to twice into, again, at, not the acceleration, the magnitude, so it'll be 5 into d. So if we solve for distance, we'll get d equals to 122.5 meter. So that's our answer. So we have found all the unknowns. It was an easy problem to solve, but there's only one catch. You have to catch that you have to take the tangential acceleration when you solve for the problem, not the magnitude. Okay. Until then, thank you so much. See you in next video. Thank you.